Oh, yes. Okay, here we are, we're finally talking about power. And we've already done some questions on that first assignment using power. And this is average power, so it's not instantaneous power. If we were working at instantaneous power, we would have to look at differential calculus, so we're not doing that. It's then work over time. And so this is where, if I have to do this work over a short amount of time, that's going to require more power than doing that same work over a long period of time. So we've finally got to the point where we can say why it's more difficult to climb a ladder than it is to walk up a ramp or up a set of stairs. In Burnie, there's that thing where you go into is it the Kmart car park, and then you go, there's the escalators, but there's a ramp as well. There's a ramp next to it. That's because it's a whole lot easier to push your shopping trolley up and down a ramp than it is to try and lift it upstairs. So that's why the ramp is there, for the shopping trolleys. It's true.
We believe you.
Can we test it out though? On that terrifying.
Are you lifting it up the stairs?
Imagine someone trying to lift their whole trolley.
Is that a bit funny, bro?
Yeah. Okay, so power is measured in watts, which is given the symbol W, and can cause a teeny bit of confusion because we've also got that W over there for work. So you have to remember that these are the units, whereas this is work. What's the units for work? Joules. Yep. So joules or J units. And this one here is, yeah, it's time in seconds. Now, it would be quite an adventure to go grocery shopping and have to lift the trolley. And I don't know why more people don't want to have such adventures, and why people are happy to just boringly just do the thing that's in front of them. All right, let's look at worked example 1. A student of mass 75 kilograms climbs stairs to a height of 3 meters in 5 seconds. So our change in height is 3 meters, and the time taken is 5 seconds. Well, we have to think to ourselves, they've climbed up, and we're given a height, so what they've done is they've increased their gravitational potential energy, haven't they? And so that means that we can calculate the energy using our potential energy relationship there. And we can swap out our E for W if that bothers us. And then we know, because we're working out power then, we're going to then divide it by, time. So it depends on the context. The difficulty with these questions is what's happening and what's the best formula to use with the information that I've been given. And so writing out the information from the question first can help you figure out the process to getting to the answer. So my average power will equal the mass times acceleration due to gravity times the change in height divided by the time, which is apparently 441 watts. Okay, and then we've got the second worked example where it's asking us to calculate the speed of a vehicle with a power output of 3,000 watts. So our output is 3,000 watts. Now, I guess another thing to keep a track of is when we're using these formulas, we are using just watts. If we're calculating energy usage in a house, it'll be in kilowatts or kilowatt hours. Okay, so just be careful that you're using the correct values in your formulas there. And we've got a frictional force of 200 newtons. And we want to calculate a speed. So here, our average power is equal to our force times our average velocity. So our average velocity will equal 3,000 divided by 200, 15 meters per second.
Where's that formula? Is that in the info sheet?
Is it on your info sheet?
It says mass times velocity.
So we've got work.
It's not, but it says W equals change in E, and then it also has power average equals change in E over T, which is W.
Okay, so you're deriving this
Yep.
relationship.